Alright, hey, welcome back. So, got another sort of semi-random video here to just kind of summarize some of the stuff I've been doing with, in particular, writing devices for SimH and integrating them into RSX-11 and trying to work with them, including working on interrupts. And interrupts have been the big bugaboo for getting this to work. As I get things working, I keep adding on to the list of things I'm trying to build into this system, so it's kind of a never-ending thing. So I thought at this point I'm at kind of a good stepping stone point. I would go ahead and talk about what I've got, and I'll push it out to GitLab over the weekend if you're interested in the code. But anyway, so I've got my my actual PiDP-11 panel, the PiDP, built and running and working great, and I wanted to mess around with that. So I've been doing the PIG bus. It's the virtual device bus. It's got different virtual devices I've attached to it and worked with for timers and a bash shell and a server and a file manager and so on. But I got all of that working finally, but it's a pretty complex system, so I thought I would make a much simpler device, something that basically just accesses the front panel, and show you all the steps and pieces of getting that installed into SimH, and then writing drivers and installing that and using it from RSX-11. So let me go ahead and just start with the bare code itself. So this is the PiDP-11 directory, and all of this stuff is in there except PiDP-11 pan, which is the front panel device that I'm going to be talking about, and the previously existing PiDP-11 PIG, which is the PIG bus, virtual device bus. So let's just look at the panel code. And my goal here was just to make a device that I can use to read the front panel switches and write the LEDs on the front panel, and then also tie it in so that when you flip a switch it will generate an interrupt, so that we could make the whole thing interrupt driven. So there's some boilerplate information in the front here. This came off of Oscar's BMP 180 hack, and this was built on top of the original paper tape punch code. I've gotten pretty far from it, but I'm leaving all of that boilerplate info in there. And then here's my standard disclaimer. This whole thing is 230 lines, and a quarter of it is just that block of comments in the front. It's really not very complex. So usual includes up in the beginning. Include the definition file. Here's the main functions that you're going to want to write for a device: reading, writing. Service I'm using for interrupts. I'm not sure if that's what it's for, but that's what I'm using it for. Resetting the device, getting help. I haven't figured out what the description is used for. I used to know, but I can't find it now. And then attaching and detaching the unit, which are no ops for us. So we need to define a few very specific symbols. And I'm calling this PAN for panel device. So this PAN, every time that we see that, is specific to this device. For the PIG, it was PIG. So the first one is IO-len, which tells us how many bytes the device is taking in unibus address space. This is taking 4 bytes, 2 words. I'm going to use 2 words: 177, 510, and 512. So that's the size of the space. Here's the base address, so it's the IO page base plus the offset 17510. And then here's the interrupt vector. It's going to be 170. Those were listed as reserved or available for the user in the documentation I had. They may conflict with other things, who knows. Just my comments here. The command and status register is at 510. The data register is at 512. Basically, if I write to the data register, it should light up the LEDs. If I read from the data register, it should give me the position of the switches. And the only thing we do with the CSR is bit 6 is the interrupt enable. So if I turn that bit on, anytime a switch gets flipped, it should generate an interrupt, and it should vector through location 170. I keep track of what our current CSR is so that I can read it back, but we don't do a whole lot else with that. And then there's a bunch of stuff that just came out of the paper tape code and out of Oscar's code. This is the device information block. Again, it starts with PAN because the device is the panel. And these are pretty much standard. I think these are generally going to be the same fields unless you're doing something really crazy. So, you know, the base address, the length, the read and write functions, and so on and so forth. This I'm setting up as a define. This is how often the system is going to check for a switch changing position so that it will know to trigger in interrupts. Interrupts are usually, you know, interrupt driven, but inside the CPU they're usually polled. And in between the steps of fetching an instruction, for example, the hardware will check to see if there's an interrupt request. So even though it's an interrupt, it's actually polled, and you can see that in SimH, the way this is set up. The unit, this is again boilerplate. And then pan underscore device, that's going to get set up in PiDP-11 sys.c. And we can hop in there right now. And it's really just, you know, declaring this to be an external device. And then down here at the end of this big array of sim devices, I just put the address of that routine in. So it goes right there. And that's all that changes in PiDP-11 sys. All right, so you can get the help command to display information about the registers associated with the device. I haven't figured out exactly in what way that's useful for my purposes, so I'm just leaving that basically null. When you say show, it will, if you put these things in here, it will show the unibus address and the vector, the interrupt vector for the device. So that's what these are doing. And show address, show vector, just return that information. And then here's the device description itself. And again, this is mostly boilerplate. I tried replacing all of this with just a 0, and it seems to work just fine. So I don't know what device disable and pan disable and unibus and qbus, what OR and all of those do. But like I say, putting a 0 in there seems to work. If you have sufficient time, you know, you can keep going through all the different parts and pieces of this kind of code and taking things out, simplifying them, replacing them, and really get a better handle on what each of the different things are actually doing. I don't need that for my purposes, so I'm just leaving it kind of the way it was in the paper tape and in Oscar's code. All right, here was the fun part. I was trying to read the switches, and you know, I know how to read those from macro. Just 177570 is the unibus address where we can read the switches and we can write the LEDs. How do I get that from a C program? Because this whole file, PiDP-11 pan.c, I couldn't figure out how to actually get that information. And at one point I stumbled across a unibus page address array, and I did a search and found location 60 octal had the contents of the switches in it, and that worked great. But then when I tried it on a different machine, it didn't work at all. So I went back and dug around the code more, and all you have to do is look at the evil globals. DR is the display register, SR is the switch register, and if I just declare these external, I can read from the switch register, I can write to the display register, and they immediately you know, are updated in real time. So globals for the win. So all I got to do is read and write those values. All right, here's the actual action routine for doing input and output. So pan underscore read takes an address, and it will read something from that address, and it should load it into the integer pointed to by data. Access, we can pull off different values like read C to see if we're reading from the console or if we're reading from code and so on. Doesn't seem to affect us, so I'm ignoring that. Basically take the address and just look at bits 2 and 1. Actually all I care about is the second least significant bit, whether you're accessing from 510 or 512. If you're accessing from 510, That's the CSR. I just take our saved CSR, write that out to data, and we're done. If you're accessing from 512, I read the switch register, store that in data, and we're done. So that's the whole read operation. And then for writing, pretty much the same thing. If you're writing to 0, I take the data that you're trying to write and I store it in RCSR. And if you're writing to 512, I take the data and I store it in the display register, and that will light up the LEDs. And then there's interrupts. So the way I'm doing interrupts, every 10 milliseconds this service routine is going to be called. And so inside here I check our CSR register, or CSR, see if bit 6 is turned on. If it is, and if we're not currently processing an interrupt for the panel device, I take the switch register, copy it into SW. I didn't have to, I could just use SR, but and I compare SW to the last panel switch that we had, and if it's different, I do two things. First, I save the current switch position in last panel, and then I call set int, and that fires an interrupt. If the last panel is the same as the switch, then none of this happens, and we come out of the if condition. And then I go ahead and I do a sim activate after, and I put in that 10 milliseconds, I think. And this will hang out for a period of time, and then eventually this service function will be called again. And so every nominally 10 milliseconds, we check to see if the switches have changed position, and if they have, we go ahead and request an interrupt. And then just a few routines at the end here. The reset routine basically removes the pan device from the SimHQ and then puts it back on there. The attach and detach are no ops, they just print messages saying that you can't do those. The help function just tells you that this is a front panel interface and what the address of the two registers are. And the description is the mysterious one that I used to know how to make it display, but I don't anymore. So that's the pan code. And then the last piece of code that we need to change is PiDP-11 defs.h. And if I just search for pan, it pops up in a lot of places. So the main places I care about, I have to describe the interrupt vector. And so all of these vectors here are for bus request priority level 4. And I can have probably 32 different values in here. These are just positions that it's using inside 32-bit int of flags. So I give it a 21 here. It's not really significant for anything. And then I use that same value to create a bit mask. So take one shifted left 21 spots. That's int underscore pan, which we'll use to check to see if this device is requesting an interrupt. And then I set the IPL level by defining IPL pan, and I'm interrupting at priority level 4. And that's it. So pretty straightforward. And then go up here, and I modified the make file a little bit. Basically, I pre-compiled all of the .c files into objects, and then now I just take these pieces that changed and recompile those. You can figure this out yourself, or you can copy this from the repository and work with it. But it makes the compilation and linking very fast. There we go, we're done. So let's go back over here, and let's go ahead and reset this. And let's play around with this. So if I show the queue, I can see that pan is on the queue, and it's going to be pulled periodically. If I let it step for a while, it's got a different amount of time until it comes up. So that's a polling that's going to keep happening. So let's do this bare metal. There's the CSR. There's the data register, and you can see I'm reading a 70, and that's the 70 that's actually over here. There's 3 switches up. If I flip some more switches, like 1770, and I re-examine, there's my 1770. So, and let me flip this over to show our display register. That should switch right there. So if I deposit, 1, 2, 3, 4, 5, 6, there it gets displayed in the display register. 1, 2, 3, 4, 5, 6. So we have access to the switches and the LEDs through this 177.77512 or 7510, 7512 on the Unibus. So we have access to that, and we can, do whatever we want. So let's set up. Let's just make some code. Move that into R0. Let's increment R0. And then move it back out to the switches, and then I'm not sure how big these instructions are. Okay. So there's a simple program right at location 1000. Read the switches, put it into R0, increment R0, move R0 back into the LEDs, and then branch back to 1000. Put 1000 in the PC and say continue. And now, all right, so I forgot to reset the processor after coming out of the previous state. So let me just go ahead and do a reset and take a look at our memory. So at location 1000, we're going to read the register, increment it, write it out to the LEDs, branch back to 1000, put 1000 in the PC, and if we do that, that should be working well now. So basically whatever value I put on the switches, it increments by 1. So there's a 6 going in, a 7 coming out. If I put 7 in, I get 8 coming out, and so on. So that's just, to kind of show that we're actually doing something. So that all is pretty straightforward. Let's look at the interrupt situation. So if I say show pan, it interrupts through vector 170. So at 170, I'll put address 200. In the next location, I'll put 200. That's going to be the new PSW, so it's going to run at a priority level of 4, which will stop interrupts at level 4 from actually interrupting. And now let's put some code at 2000. Let's just put a halt, and then do a return from interrupt at the next location. And that should be all we need. So if I go ahead and run this, it acts like it did before. I can flip switches, and it adds 1 to the switches, but it's not interrupting, right? So I need to actually enable interrupts. So let me stop this and put a 100 into our CSR, and then continue. Let me straighten this out again. And now if I flip a switch, you see it goes to halt. And I can hit the continue button to continue, and it's in the run state. And if I flip another switch, it halts, and I can continue from there. And if I flip another switch, it will halt, and I can continue. So interrupts are working, right? Anytime that that a switch changes, it goes ahead and detects that, and vectors through 170. 170 goes to 2000. And 2000 is where it executes the halt instruction. So interrupts are working fine. So this is all great at the bare metal level. Let's take a look at it under RSX. All right, so I'll quit out of here. I'll go ahead and run PDP. And I flip the switches to turn on switch 1, which says boot into RSX-11. Date and time, so I made a hotkey combination, Control-Alt-D, which will type in the date and time in the appropriate format, so I don't have to keep typing that in or defaulting to 2018. And this will take a minute. This will come on most of the way up. It'll ask about LAN and TCP. We can say no on those. And it's just installing different programs at this point. We'll say no and no, and there we go, we're up. I'm going to want to run with a VT100 emulator better than what I can get out of console, because I want to use the keypad when I'm editing, and PuTTY seems to be a good way to do that. So I can run a pp command, which will open a PuTTY session, and in PuTTY I can go ahead and log in. So I'll just log in as Nick, and I get the login message on the console over here, and now I'm in the system. So let's take a look at this code. The first thing I want to do is look at the actual driver code. So you need two pieces of code. This is again, you know, work I've leveraged other people's work for this. You need a driver file and a table file. So I'm calling my device QF for front panel, and so let's go ahead and edit QF drive.mac, and we'll go into full screen mode. So this is QF drive. This is from Lee Gleason's BMP-180 driver that he put together to show how to interact with devices through RSX-11. Also there's a guide to writing an I/O driver. Chapter 6 in particular is especially useful. Again, most of the stuff is just going to be boilerplate. So LD $ and the name of the device QF equals 0. That makes it loadable, I guess, as opposed to resident. The device driver table needs a few arguments, QF1, some missing arguments, and a T. Here's a load entry point. So when I load this device into the system, whatever code I put here will be executed. I'm just going to throw a magic number out to the display just so we can see something happen when we load. And I'll switch over to the display register just for kicks. Looks like it's already got 1, 2, 3, 4, 5, 6, so that doesn't make sense because this isn't loaded as far as I know. Right, so QF : is not in the system. So maybe load happens earlier than I thought. Anyway, my interrupt handler, so I've got a QF int entry point. That's what's going to get called anytime an interrupt happens. And there's some things we generally do. I don't necessarily need them because this is a really simple interrupt routine. But we do an interrupt save, which my understanding is saves the current state of the system, including the registers, sets a priority level. I don't know, 5 or 4 is the right thing there. And this is just a constant. I think it's a 1 or a 0. My actual code, I'm just going to increment an integer interrupt count and display that on the front panel. So every time we get an interrupt, we should see a counter bump up. If I wanted to leave, I could jump to int exit. If I want to do more things, I can call $fork. And I think what that basically does is it makes a new kind of a process, a little bit like a fork, that runs at a lower priority so that I can do things like, you know, more complex interactions, things that take longer without the whole system hanging out at this higher priority level and bogging everything down. When I'm done, I'm going to go back to the entry point for all of this, the initialization point, QF_ini, or I could just return if I wanted. QF_ini is where we go when someone does a QIO and we check to see if there's work. I can also define functions at all of these different points. In particular, if you do an IO kill, you'll jump to QF cancel. But there's other things. There's the power fail entry point and so on. These are all going to be no ops. I'm just going to return. Here's the action routine, QF_ini. We call get packet, and when you make a QIO request, you specify basically a buffer that contains information you want to pick up. So let me go ahead and actually take a look at that over here. I've got a qf test.mac, and I'll go through this more in a little bit, but basically when I want to do a QIO, I load up some value in this buffer. It's a 2-word 4-byte area, and then I call it QIO and I specify the buffer, and that brings me down here, right? QF-ini. Get packet will pull off the first word of that buffer, and if there's nothing in there, if there's, sorry, not the first word of the buffer, first word of an IO request, if there's nothing in there to do, my carry bit will be set, and I'll just go ahead and return. If the carry is clear, I come down here, and I can check the function code. So R1 starts a block of data, and if I go to this offset, I get the function code, and the function code is the full function code shifted right, so we divide by 400 to compare. So if I'm doing a read logical block, this will be the value I find. If I'm doing a write logical block, this will be the value. So I jump to either do read or do write. If there's any other function code, I don't have anything to do, so I'm just going to go ahead and put this value into R0. That'll be my return value, and I call IO done. That should finish the QIOW call, and then I can go back to the beginning, QF-ini, and look for more work to do. And then do read and do write, pretty straightforward. So this is where we're picking off the pieces of the buffer. So do read, R4 comes in. If I go off s.csr from there, I get to the actual CSR, the base address of the device. Get word will read the first word in this buffer and put it on the stack, so then I can pop it off the stack into R1. The way I'm defining this interaction, this buffer, the first word is the index of the register that I'm working with, and then the second word is either the value I'm writing or a place to store the value that I read. So I call get word, pop it off the stack. R1 is the index. I mask off everything except bit 1. I add it to this base address R2. R1 is the actual address I want to query or write to. In this case, I'm reading. So I want to query R1, read the word from there, push it onto the stack, and then I call put word. And put word will push that into the second word of buff. So so if I'm doing a read operation over here, here's my read, here's my buffer. I put this magic number data, which is just a 2. It's just defined to be a 2. So I put that into the buffer, and then I do the QIO with a read logical block. I can check the IO status block. That should come back non-negative, and then I take buffer plus 2, that's where this put the word, and I store that into R0. So that's how I read the switches, and then I branch to successful return over here. When I'm doing a write, it's almost the same thing. Offset from R4 to find the CSR address, get a word that gives me the index to the register I'm interested in, pop that off the stack, put it in R1, mask everything except bit 1, add that to the base address. R1 is now the address of the register I want to write. This time I call get word again, which gets the second word of the buffer, puts it on the stack, pop it off the stack, and store that at the address pointed to by R1. That's how I write the register, and then branch to success. Success, I just take the success value, put it in R0. I don't think I have to do these other things with R1 and R2. I call IO done, that finishes the QIO operation, and then I branch to QF-ini, which will go back and look for more work. So that's pretty straightforward, right? That's the QF drive.mac, and then there's a table that goes along with that, QF tab.mac, and this one is even more just kind of magic words. Preset code that we just do because this is what we do. So QF table equals 0 makes it loadable. Here's the database, here's the device control block, and most of this, you know, QF0 because it's the QF device. Here's the actual ASCII name QF, 2 characters, starting from 0 to 1 minus 1, so there's only one unit, unit 0. This will calculate the length of the unit control block by subtracting the starting and ending locations. This points to the driver dispatch table. And then this part you have to write depending on what you want to do. So I just wanted 3 functions: read logical block, write logical block, and kill. And if you look in the guide to writing a device driver, you'll see the mask values for that. And basically it's just the first 3 bits. So 1, 2, and 4. So this is a 7. Bit 1 is the kill function. That's a control function, so that goes here. Everything else I just made 0. And I don't know if that's right or not, but it works. So I'm running with that for now. Here's the start, where it's going to calculate the length of the block. This I have no idea what it does. These are all, just taken from examples. And they seem to work. Here's the end, so it'll calculate the length of the unit control block. And then here's the action point, beginning of KRB SCB. I want the interrupt vector, so that's going to be priority level 4, and the vector is 170 divided by 4. And then the unibus address 177.510. So those are both critical. This points back to QF0. Most of the rest of this is just the same. QFA, because it's a QF, that points back up top. There's the name QF again, and that's pretty much it. So without really understanding what most of that does, you can still write it successfully. And then you have to build this thing. So make good use of your tools. The commands for assembling and then linking and the task builder and all that can be kind of hairy. So I made a command file, build driver bdrive.cmd, that does all of this work for me. So I can say build drive space QF, or I can just say build drive, and it will ask me what the 2-letter code is for the device I want to build. So that goes into FN. Here's the assembly code, so MCR macro, in my case QF drive equals, point to the EXEMC, point to the RSX-MC, and then put in the source code, qfdrive.mac. Check the success status. If it doesn't succeed, error out. Do the same thing for QF tab. Check the success status. And then I need to build a command file for the task builder. So I open up a bdrive command.cmd, and I just write these lines into them. So there's QF drive. I don't remember what all these switches do, but they make it work. And again, this all came from documents that other people figured out. And then I do a task builder, and I give it that command file, check the success status. If it succeeds, then we go ahead and we copy qfdrive.task and .stub into 1,54, and then we have to install it. So I use this install drive command that I give a 2-character code to, and if it succeeds, I'll go down to 999. Otherwise, I'll print an error message. So then these are just the different error messages. So the install, gotta be able to type third time. So the install is doing a number of things. First of all, it checks to see if the device is currently loaded, and if it's not, it doesn't worry about it. But if it is, it will take it offline and then unload it, and then it will load it and bring it online, and then it will show me the device. So if I want to build this, I can just say bdrive QF, and it does all the things. And that automatically installs it. If I make, if I'm on a new system and I want to install it from scratch, I can just say install driver QF, and it goes ahead and comes up. So now if I do dev QF, it tells me it's loaded. Alright, so So that's nice. Oh, and there's some cases where you actually do need to reboot. Changing the driver code itself, you seem to be able to unload and reload, and it works fine. But if you change the interrupt vector or the unibus address, those seem to be persistent somewhere. And I can recompile everything, reassemble everything, unload and reload, and it's still using the old vector or address. At least that's what it looked like for me. So in some cases you do have to reboot to load new changes in. But if you're just making tweaks to like qfdrive.mac, seems to be fine to just uninstall, reinstall. Alright, so let's take another look at this code, qftest.mac. And so I've set up some symbols for the command status register and the data register. Here's a few variables I'm going to be using, so I put them in a data section. Here's the start of my program. I'm assigning the QF device to logical unit number 1, so I put a 1 in QF-loon just so I don't have to hardwire 1s everywhere. And then assign logical unit number QF-loon. Here's the name of the device, QF. And then if the carry is clear, it's succeeded, so I'll go ahead and branch to good stuff. Otherwise, I'll go ahead and exit. Good stuff, this is just going to be a loop. So we're going to do the same loop that we did before. I'm going to put the data index, which is index 2, put that into buffer. And I'm going to call QIO with a read logical block. That should read the data register, put it into buffer +2. Just for kicks, I'm testing the IO status block, making sure it's not negative. And if it's okay, then I go ahead and I move buffer +2 into R0. I also test R0, and if it's equal to 0, I'm going to exit. So that's going to give me a way to get out of the program without aborting. I can just flip all the switches down, and it should exit right away. Otherwise, I'll increment R0 just for fun. And then again, put data in the buffer register. I'll put the new value of R0 into buffer +2, and I'll call QIO write, and then I'll go back to the beginning. So assembling, made another command file called M, and it's the same idea. See if there's an argument. If there isn't, ask for a file name. Otherwise, go ahead and do mcr macro file name equals filename.mac. Check the status. If it succeeds, I go on down to 400. If it fails, I reassemble, but without putting in a listing file. The advantage of that is it will show me any lines with errors on them on my display, so I don't have to go through the list file. And then I do the task builder, file name equals file name. If that succeeds, I go ahead and I run my program. So I can do add m qf test, and there we go, it's running. And you can see up here I've got my first switch set, but it's showing a 2 on the display. And so I can flip the switches around and see exactly what's going on. It's always adding 1 to the value of the switches, and that's pretty cool. And then if I set the switches to all 0, it exits at that point. Alright, so we can interact with the device through its unibus registers by using QIOs. We can do this from BASIC, we can do it from Fortran. You can see other descriptions of that. But let's look at the interrupt piece now. So I'm going to change qftest.mac, and I'm going to put something up here in the beginning. When we get to good stuff, I'm just going to jump down to the end of my program to interrupt enable. And interrupt enable is going to go with the command status register, so put a 0 into buff, put 100 into buff +2, call QIO write, and then it will just go ahead and exit. So let me go ahead, build that and execute it, and that's good. But now interrupts are live. Now the system is still working. right? Everything's fine. But remember what our interrupts do. If we look at qfdrive.mac, what should happen is when an interrupt occurs, we should come down here to qfint, and basically it's going to add 1 to this interrupt counter, put that out on the display, and then that's basically where it exits, goes back, looks for more work. So just kind of sitting here, you know, not running any code per se. If I flip a switch, we'll see our number display 1, 2, 3, 4, 5, 6. And basically every time I flip a switch, it generates an interrupt. And we can see that it's generating interrupts by the fact that our display register is counting up. So we've got interrupts running under RSX-11 in a very controlled way, which is kind of cool. And it's pretty straightforward to wire that up, because we have this entry point that that is called every time that an interrupt occurs, just this qfint. So what gets wonky is when we try to generalize this, because I decided what I really wanted to do was be able to write a piece of macro code that not only interacted with the registers but allowed me to specify an interrupt handler myself, because I don't want to have to go back and change the driver and rebuild that and reinstall it and stuff every time that I want to, you know, do something different with an interrupt. I wanted to be able to do like we do on a Raspberry Pi or an Arduino, just write some code and say, hey, when an interrupt occurs, run this function. So I want to work basically with an AST handler, an asynchronous system trap. That turned out to be more confusing than I hoped, and I'm able to get that to work eventually. That's going to be a different video, but I can show you the basic punchline for that. All right, so yeah, we can take a look at what this looks like. And like I say, I'll do another video and push some documentation out for this later. But basically, here was some nicely bundled code for doing all of this stuff through some macro files that find a number of macros. So this was just a simple test of two alarm devices running at different rates. TT-init lets me do I/O, print messages like pmessage, or to print numbers with pnum. Basically, I assign 2 devices for the PIG bus, one for actually interacting with the registers and another just for handling the interrupts. And I'll tell you why in a minute. But I picked 2 logical unit numbers, 1 and 2 in this case. PIG arm lets me specify the address of a function and say, hey, that's my interrupt handler. And any time that the PIG bus throws an interrupt, it should jump down to this function myHand. If there's a problem with that, the carry will be set, and I can detect that. And then basically I just have these functions put and get, so I can put things into the slot register, the CSR, the data, or the aux register, and I can get from those registers. If I say put, it takes this value and puts it in there, and that can be a number, or it could be a memory location or whatever. I also have the option when I put of putting some additional flags on. So this says I want to put a 1 into the CSR, and I want to wait for a flag to go to 0, and the flag I'm looking for is just CSR masked with the mask 1. Up here I'm putting a 2 into the CSR, which is setting the time of it, right? I'm loading this number, hex 401, into the slot register, and then I'm loading this number slow, which is 200 for 200 milliseconds, into the data register. Putting a 2 in the CSR says write the time, and I want to wait until bit 7 of the CSR is turned on. So I say write a 2 and wait until the mask is not 0, and the mask is 200. So this basically sits there and spins, checking the CSR until bit 7 is a 1. So this lets me very easily make changes to the CSR and wait for certain bits to either be set or clear without having to do a lot of testing and looping and so on. So it's optional parameters on these put commands. throughput CSR. So so I load a slow time into alarm 1. I load a faster time into alarm 2. I enable interrupts on both of these devices, and I also, in the very beginning, I put a 1 into slot 0 CSR. That enables interrupts for the entire bus. And then I'm also using the LCD panel, so I have this LCD display up here. There's no way I can read it with this camera. It's just too washed out, but it's a little 4 line by 20 character LCD display that's accessible through the PIG bus. So I put that into slot 3, I give it an initialize command, and then my whole program just sits here and spins, just hangs out and waits. When I get an interrupt, I'll come down here to my handler and PIG pre, save some registers, does some initial checking, read the current slot, the current value of the slot register, just in case I was doing more interesting things than just spinning. I save the current slot I'm looking at in a temporary location. I can print messages using pmessage. I can print numbers using pnum. I was having some problems before, so I was looking at the stack pointer. And then if I go to device 0, so I look at, I put a 0 in the slot register. That means I'm talking to the PIG bus controller. If I read the data register, that'll give me the ID of the device that just interrupted me, and this will say, you know, who I got the interrupt from, and I can see if it was device 1 or device 2, which is where I put the 2 alarm clocks. If it's neither of those, I'll print an error message and continue at handler done. Otherwise, if it was the first device, I increment int1's counter, and I go to the display section. If it was the second device, I increment int2's counter, and I don't have to go to the display section because that's the next line. Let me put these prints back in because, like I said, it's hard to see the LCD output, but I'll print the 2 counts with a space in between. I was playing around with hanging out in the handler for a large amount of time to see what happened if interrupts got stacked up and so on, so I had some code here for spinning. I'm not doing that anymore. I'll display on the LCD panel. I'm not going to go through the details of that, but basically we convert the numbers into strings and show them out 1 character at a time. And then handler done, basically we rearm. So I say pig arm and give it my handler. We make sure we do that before we acknowledge the interrupt. So when we set bit 2 of slot 0 CSR to a 1, that's the interrupt acknowledge bit, which allows interrupts to occur after that. We restore whatever slot we were looking at before the interrupt, and then pig post takes us out of the interrupt handler. So all of that, and I can build it, you know, with my M macro, and it will link it and it will run it, and you can see I'm getting an interrupt count. Here's the slow interrupts on the left, here's the fast interrupts on the right. And so I can work with interrupts, and when the interrupt occurs, it calls an ASC, just a function that I've defined, and I can do whatever I want. I don't believe that's doable from BASIC. I believe it is doable from Fortran, but I haven't tried actually passing that, passing the address of a BASIC function or subroutine through the QIO in BASIC. That would be kind of cool if you could do it though. But anyway, there we go. So that's all working fine. That's a whole separate discussion how the details of this work, and it ties into using the QIO kill function to trigger the cancel. But anyway, it's totally doable. Oh, and let's see if we can actually like look at the LCD display. Yeah, now it's pretty fuzzy, but oh, there we go. So that's just outputting the same numbers that are being printed, just for fun. So, all right, cool. That's all I got. Lots of blinking lights there. Thanks. Talk to you later. Bye.